So in this video, we'll be taking a little bit of time to talk about what is known as a unit vector. So if you look at the definition here, any vector that has a magnitude of 1 unit is referred to as a unit vector. So, much like the unit circle has a radius of 1 unit, and you've used that to do different things with trigonometry over the years, a unit vector also has a magnitude of 1 unit. There are two unit vectors that we want to take the time to define up front, and we'll be working with these throughout a lot of the problems that we do throughout the rest of this video. So the two vectors that we're going to take a moment to define here, they're referred to as the standard basis vectors, and the two-dimensional standard basis vectors, you'll add one more to the mix when you get a third dimension worked in, but the two-dimensional unit vectors are denoted as unit vector I and unit vector J. You might notice this little hat symbol that I've placed on each of those. When we see that symbol above a letter which names a vector, that symbol is specifically used to denote that that is in fact a unit vector. So you wouldn't use this symbol on a vector in general unless you're 100% certain that it's a unit vector. Vector I and vector J are defined to be unit vectors as we see on the screen right here. So if you look at what unit vector I is defined as, it's defined as a vector that has an x component of 1 and a y component of 0. If we did a magnitude calculation for this, we would definitely get a magnitude of 1. And if you think about what unit vector I looks like, it's just going to start at the origin and terminate at 1, 0. So the entire portion of this vector is working its way in the x direction, and then unit vector J is kind of the complete opposite. The entire magnitude of vector J is working in the y direction, and then the x component of unit vector J would be 0. Again, these are called the standard basis vectors, and we'll be doing some work with those throughout the next couple of problems. So here is a quick example where we're going to take the opportunity to take a vector that is not a unit vector, but write it in terms of the standard basis vectors. So a lot of the work that you might do in a physics course, in an engineering course, you'll benefit by having the opportunity to use matrices and different operations with those. And just depending on the professor you have, the textbook that you use, you might have a textbook that uses this notation, or you might have a textbook that uses this notation. So if you look, the start and finish of this are the exact same. It's just a different way of expressing the initial vector. So we've definitely looked at this a little bit throughout our introduction to vectors here. And if I think about how I can break this vector up into a sum of two separate vectors, I can break it up so that the x component of 1 is shown by the first vector and the y component is 0. And if you think about why this is something that's useful to do if we're trying to get the unit vectors I and j involved here, this right here is the unit vector I. So you'll see on this next line, I replaced that initial vector with just unit vector I. The next vector, I did something similar. It was a bit different, though, because we didn't have a magnitude of 1 in this position for the y component. We do have a magnitude of 0 for the x component, but if we wanted a magnitude of 1 here, what I'm going to have to do is I'm going to have to factor out that 2. So if I factor 2 out of the two components of the second vector, what I end up with is 2 times unit vector j. And if I wanted to express the initial vector in terms of the standard basis vectors, what you see highlighted here at the bottom is how that's done. You don't obviously have to go through this sequence every single time. If you think about what the shortcut would be, the x component is 1, that's the coefficient of unit vector I. The y component is positive 2, that's the coefficient of unit vector j. So, I did some of the algebra with vectors to show the progression, but you can definitely just go from start to finish. This is going to be the coefficient of unit vector I. This is going to be the coefficient of unit vector j. The sign in between is going to be whatever the sign of the y component of the initial vector is. So here's a problem from the textbook. Asks us to do two things. We want to find a unit vector that goes the same direction as the given vector, and then we want to write the given vector in polar form. So we'll tackle part A first here. So we want to find a unit vector that travels the same direction as the given vector. Now notice how this vector was presented. It's presented in terms of the standard basis vectors. what we just talked about should hopefully allow us to recognize that this vector, this standard basis vector presentation, is actually equivalent to an x component of positive 2 and a y component of negative 4. So here's the component-wise method of defining that vector. But if I wanted to find a unit vector that goes the same direction as the given vector, the process here is to actually take the vector that we start with and divide it by its magnitude. If you divide a vector by its magnitude, that divides the magnitude down into a 1. And so if we wanted to try to find the magnitude of the initial vector, I'm going to do my Pythagorean theorem calculation with those components, 2 and, yeah, technically it should be negative 4, but we're squaring, so it doesn't really matter, which gives me root 20. You see this next line, I'm using the original presentation of these vectors, the standard basis presentation. So what I said 30 seconds ago was you're going to divide the original vector by its magnitude in order to turn that into a unit vector. Well, dividing by the magnitude is the same as multiplying by 1 over the reciprocal of the magnitude. And that's pretty easy to do here because we can just distribute that into both coefficients, which gives us an x coefficient of 2 over root 20. And that would be the coefficient of unit vector I. And then the coefficient of unit vector j would be 4 over root 20. Yeah, these fractions here simplify a little bit, but just kind of pay attention. If your professor, your teacher is going to require for you to, rationalize and get rid of the root that's in the denominator. If you're one of my students, I'm fine with you leaving your answer looking like mine looks on the screen right here. Part B asks us to write the given vector in polar form. So this might be the first time that some of you are hearing about polar form. For those of you that have already taken Calc 2, Calc BC, you'll definitely already have some familiarity with this. So a polar coordinate is not an x comma a y, right? That's basically how this vector here is presented in its component-wise form. A polar point is defined with a radius, which is simply a distance from the origin, and an angle, theta. So if I'm trying to express this vector in polar form, you see I redrew the vector down here in blue. The radius, the distance that this point is, 2 comma negative 4, the distance that terminal point is from the origin, is simply going to be the magnitude of the vector, right? I would apply the Pythagorean theorem to find the magnitude of this vector. So I already did that calculation back in part A. The radius, the distance that point is from the origin, is square root of 20. What about the angle? Now the angle that we open up with, just like you've done with your trig work and your work on the unit circle, that's going to be an angle that's measured from the positive x-axis. So in this case, and I see a little issue that I'm going to have, we'll try to fix this up here as we talk about it. What I did is I basically kind of redrew what's in the coordinate plane here as simply a triangle. I realized that this was 2, this was 4, and I recognized that SOHCAHTOA would allow me to figure out what that angle was. So I grabbed tangent, set myself up an equation, solved for theta. The issue that I didn't take into account when I was putting this slide together that I was lucky enough to catch as I've been talking about it is this. This angle, since I'm dropping from the x-axis, is definitely going to be a negative angle. So inverse tangent of 2 is going to be a positive answer. I would need to define a negative value for that. Alternatively, what I could have done, and this was just kind of, I guess, a little laziness on my part, normally when I draw triangles, I don't attach a sign, S-I-G-N, to either of these values. If I would have had a negative attached to the 4, which it really was, then this would have been a negative 2, and that will allow me to get rid of these negatives that we had to insert. So I'm going to leave what I had in there initially. Either of those would definitely define a negative angle. So I have the non-calculator version of this on my screen right now. If the calculator's in play, you can figure out what inverse tangent of 2 is, make it negative, and just double check and make sure that that does seem like the number of radians that you would appear to be dropping from the x-axis there. But when you're defining an angle, when you're defining a vector in polar form, the individual components of that vector are a radius, which is a distance from the origin, and a theta, which is an angle that you're opening with from the positive x-axis. Last example that we'll check out here asks us to find a vector with the given magnitude that goes the same direction as the given vector. So what we're effectively doing here is we're allowing this vector, v, to provide direction. And then we don't necessarily want the same magnitude as v, though. We want a different magnitude. So we're allowing a known vector to provide direction, but then we're forcing our resulting vector to have the magnitude that we desire. So the procedure for this is to basically find a unit vector that travels the same direction as the given vector. So like we did in the previous example, what I'm going to do is I'm going to figure out what the magnitude of that initial vector is. So I do a quick magnitude calculation for vector v, so a little Pythagorean theorem going on here, and we end up with square root of 10 for the magnitude of vector v. Now if I want a unit vector that goes the same direction as vector v does, I'm going to divide vector v by its magnitude, or multiply by the reciprocal of the magnitude, and that'll end up giving me this vector. So the vector that you see right here is a unit vector. It is guaranteed to travel the same direction as vector v does, because it's got the same proportion of it moving in the x direction as vector v had moving in its x direction, and the same proportion as vector v had going in the y direction for it. So this vector is a magnitude of 1 since it is a unit vector, or it has a magnitude of 1 since it is a unit vector, but it goes the same direction as vector v does. So we've got a unit vector the same direction as vector v. Well, if we want our resulting vector to travel the same direction as vector v, but to have a magnitude of 10, we're going to allow this unit vector here that we just determined to provide direction, and we're simply going to multiply by the magnitude that we want, which is 10, in order to develop that resulting vector. So this vector that you see here, it's going to go the same direction as vector v does, but it's going to have a magnitude of 10. You can double check that. You can apply a magnitude calculation to this, and you will see that it has a magnitude of 10. But this is something that's a nice way of allowing an ordered pair or a known vector to provide direction, and then to have it take on a certain magnitude by multiplying by a scalar.